I need to point out that general.
He has some check mark as if he understands.
Yeah. General chemistry is actually going through chemical bonding right now, which is what you guys just went through. It took you 2 weeks to do it. It's going to take them less than 4 days. That being said, when you see things like that, don't ask the same questions. They're definitely not. They're just going to learn like trigonal, planar, linear, tetrahedral, maybe pyramidal, and call it good. And they're not going to go through hardly any of this. Like none of this is. They're not even going to learn this, none of this, none of that. I'll tell them about Vesper. They're not going to have to know anything about it. So when you see that, you might see, it might be confusing a little bit of why other courses are going through the same thing, but you guys are way deeper than anything they would do. That's a good thing for you guys, right? Then I say, please help general chemistry. If you see them struggling on homework, go ahead and be like, hey.
And no, I'm going to laugh at them and be like, haha, I remember when I took that class.
Remember that, I did that. We all tried. Okay, enthalpies is the last thing. You've actually seen this already, so you don't necessarily have to write this part. I'll tell you when you should consider writing. You can write this if you want to, but remember your phase change diagram. So this is the one, if you look back at the beginning of your notes, you did something like this, right? And I won't worry too much about the lengths of these or the size, the angles of the slopes. We're just trying to make a general point.
That is ugly.
So solids, liquids, gases.
It doesn't even fit in the
What do you mean it's ugly?
Look at the end of the bottom line.
Well, I mean, we're just going for general idea here.
That didn't even.
How is that not?
It doesn't fit. Do you see how long your top, like, the actual graph is? And then.
There we go.
Thank you.
Okay.
Yeah, thank you.
I'm glad we can move on. Two fundamental equations, Q equals ms
Delta T.
where Q is the amount of heat, energy added or removed from a system, M mass, S specific heat. So this is the quantity of thermal energy or energy required to raise a specific amount of a substance by a specific degree. So 1 degree Celsius, in essence, is what we're going for there. This is the change in temperature. Because of this factor alone, whenever there is a change in temperature, which would be this general region, right? Then you can use this equation. However, if you notice, the temperatures all along these positions are the same, and if there's no change, then what's the value of Q? No change, the value of Q would be 0. And now that would be weird because it'd be like you're doing something to the system to get it from a solid to a liquid, but you have no change in heat energy, right? So then we said something to the effect of, we can actually measure the amount of heat energy as it relates to this value of enthalpy. Remember this equation? And then
wasn't it for like potential kinetic energy or something?
Yep.
Like that?
So you're changing the potential energy, the bond nature, and you're increasing the speed at which atoms move. So kinetic energy, potential energy is here. So notice there's nothing about a change in temperature. We just need to know something about the enthalpy of fusion, vaporization, solidification, etc. So we said something like this. If you move this direction, this is the heat of fusion, the enthalpy of fusion. If you go the opposite direction, that's the enthalpy of solidification. So this is the quantity of thermal energy, specifically heat, needed to move from a solid phase state to a liquid, or to go from a liquid back to the solid. The relationship between those was established that delta H fusion is equivalent to delta H solidification. The only difference being one of these has to be negative. So you choose which one. Is this endothermic or exothermic though? Fusion. Endo, gaining energy, and then exo. So by nature, this is already a positive, and this is a negative value. That cannot be true, that positive is equivalent to negative, so oftentimes we just introduce a negative sign into a mathematical function to carry the expression, to introduce a constant, something of that nature. So now it's an established relationship. Yeah.
Why can't you just do the absolute value?
You can do the magnitude of those values is equivalent. That's true. Yeah.
Is it solid or solid?
Solidification. Yep. So going back from the liquid to the phase state. I just abbreviated. Yeah.
That is not even how you abbreviate.
Okay, wait, question.
Oh.
The N stands for moles?
Yes. And this is the quantity of material present. So in essence, if you had the knowledge of the mass of something, you could get that to the molar amount. Or, likewise, if you had the knowledge of the volume of something and you knew something about the density, you could get to the mole amount. So it doesn't matter if you're given a specific quantity as it relates to a volume, or if you're given a specific mass, we can still find in the value of the moles. Yeah.
Okay, follow-up question.
Yeah.
How do you know which enthalpy to use? Because on previous
Yep.
tests and quizzes, it's always been like find
Yeah.
the thingy
Yep.
of the specific heat, but it's like ice. So
Sure.
how do you know which
Yeah,
enthalpy to
absolutely.
use?
So it depends on which way you're going. So if, for instance, you have a sample of a substance, let's say at -25 degrees Celsius, and you raise the temperature of that substance, let's say to 0 degrees Celsius, because there's a temperature change here, you're going to go this equation, you don't even need to use enthalpy. However, if the question then says, consider 50 grams of water at 0 degrees Celsius, what is the quantity of thermal energy required to undergo a phase transition? So and maybe I should add another sentence there, to undergo a phase transition to a liquid phase state. That last part would say use the fusion because you're undergoing the phase state transition to liquid versus trying to make it go back to a solid. So I would have to give you enough information to know which direction you're heading so you can isolate the enthalpy of choice. But fortunately, you're not using this curve in this chapter. The reason I'm showing this is because we're going to deal with these delta H symbols extensively, which is enthalpy. And they're going to tell us something about the bonding nature of molecules and the relative stability of the complex or the structure that's formed ultimately. Yeah.
Okay, and how do you know which specific heat to use? So if
Yeah.
it's like -25 degrees to 0 degrees.
Right. The S could be for the solid phase state, it could be for the liquid phase state, or for the gas, which is what you're alluding to. It depends again where on the curve you would be at. So if you're at the -25 to 0 range, you want to use the specific heat of solid ice. If you're in the range of something like 2 degrees Celsius up to 99 degrees Celsius, you'd use specific heat of the liquid. And any temperatures above that, that would be the gas.
So it's the final temperature that determines what kind of specific heat we use?
The range is important. So the given here, it doesn't necessarily matter the 25 or the 0, but as long as you're occurring somewhere in here, you have to use the solid.
So if it's -25 to 99 degrees,
I wouldn't, because that would be 3 different calculations. You'd have to do one with the specific heat of solid, then you'd have to change it and do a temperature range using specific heat of a liquid, and then change it again to do the gas. So you'd actually end up using all 3, but as 3 separate calculations, and then add all the answers together. Yeah, but again, we won't need to do that this chapter. Yeah.
So we're only gonna use the Q equals.
We're going to use this
delta H.
enthalpy value. The challenging part, and you don't need to go there, what's going to end up happening, if you look at the course schedule, I sat back down this morning and changed all the dates. April 15th, you have no school, that's Good Friday, and then the following Monday is a professional development for teachers, so you have no school. It's a 4-day weekend. So on April 14th, I think I have you taking a short quiz over redox reactions. That's where we'll be at that time. And then I'm going to bring you back to this thermochemistry. This is called thermochemistry. Thermo for heat, chemistry, what's the heat exchange as you're doing chemical reactions. I'm going to bring you back to these concepts. So you have the 4 days to kind of be like, take a little breather, refresh it, re-see it again. Because if 50% of the ACS exam arguably is math, of that 50%, a good portion, probably 20% of that 50 is actually coming from enthalpies and calculations. So it's good for us to see it multiple times, not all at the same time. You know what I mean? See it at the beginning of the year, see it now, see it in a couple weeks from now, and it just keeps it fresh, kind of back there in the back of your mind. This relationship, that Q, is actually the same thing as enthalpy, has been solidified through a little bit of what's called a derivation. So if you think about a derivation in math class, you can take the functionality of an equation and take another one and eventually derive a whole new fundamental equation together, right? But it takes some work to ultimately get there. So this expression is true for us. In essence, what we're saying is heat is enthalpy, and enthalpy is heat nonetheless. So that's how we used these equations previously. The big picture here, just to say we've used it, is now to officially look at what's called Hess's law. And we did that like this. We set up some situation where we looked at the enthalpy exchanges. If this was to go up to here from solid to liquid, and that's delta H fusion, to go from the liquid to the solid, right? That's delta H solidification. What is it to go from liquid to gas? Delta H what? The enthalpy of vaporization in the reverse. So is it true, let's say it like that, that the enthalpy of sublimation is equivalent to delta H fusion plus delta H vaporization? Is that a true statement? Yeah, right? That's called Hess's law. And we originally, I think we said it, I don't know that we ever wrote it like that, but that is a very delicate equation, meaning it's simple, it's straightforward, it's just an addition process. But delicate meaning if you took the value of delta H solidification, that would actually be a negative value. And if you take a negative and add it to a positive value, that's not the same thing as taking a positive and adding it to a positive, right? See what I mean there? The sign conventions are delicate. You have to keep track of which one ultimately. So Hess's law says the total enthalpy for a reaction is equivalent to the exchange of heat energy, the enthalpy of, let's say, process 1 plus process 2 plus process 3 plus process out to infinity. That's all he's saying.
Wait. Say that slower.
Yeah. Any individual heat exchanged in an individual step. So this could be like step 1, plus the individual heat exchanged of step 2. So here's step 2 is equivalent. So the summation of that is equivalent to the overall heat exchange for the process you're looking at, which would be here, delta H sublimation. So this is delta H of the reaction is equivalent to 2 individual steps. This is called a state function. The state function legitimately means it doesn't matter how you got there, it is going to be the same response each time. So for instance, if I want to walk to the door, right, and I want to say, and don't write this down, this is the physicsy language just as a comparison. Actually, let me use an example. This is a track, 400-meter track. If you start here at the start line and you run 400 meters around the track, that is the language we would use would be distance. Okay, you ran 400 meters. Could you have run further and still ended at the same spot? What do you think? Not a trick question, but could you have run further than 400 meters, but started and ended at the same spot?
Yeah.
What would you have done? You can't leave the track. You have to stay on the track. But what would you have done?
Run
Forward. What did you say? Go back or forth or what?
Run all the way around the track.
You could do something like this, right? And then you would have run, I mean, that would have been stupid. It really would. You would have run almost like 450 meters or 500 meters, but you ended at the same spot. That language of start and end at the same spot is a word of displacement. So where did you begin and where did you ultimately end is the same spot. So if I look at that as the door, the displacement from me to the door is 10 meters. But I could certainly walk all around this room and end up have walked a mile legitimately before I got to the door. So state functions are very similar. It ultimately just says where you began and where you end is important. It doesn't matter the path you went to get there. It's always going to be the same, right? That's in essence a state function. Some other things that are not state, if you think of things that are not state functions, work is not a state function, meaning if I push on this table a little bit and I push on it harder and even harder and harder and harder, my work is getting greater and greater and greater and greater and greater, right? But if I push on this table a little bit and then pull on the table and then push on the table and pull on the table, ultimately did the table move? The movement of the table is a state function. It's independent of how I pushed on it. It's either in the same spot or it's not. So more to come on that later. Why I say that now is legitimately because it's a process. Just add up the individual steps, and that is the important part. eventually using state functions derives this equation, but we're not going to derive this. We're just going to assume that somehow, and we could do the math, it's not beyond you guys, it's just not in the scope of what we need to do today, or any day really, but we could get there, okay? All right, so Hess's law, here's where we can begin with that. This is, if you're looking at it, I think this is the Born-Haber PowerPoint on Google Classroom, if you want it as a reference, or so you don't have to rewrite everything.
Oh my goodness, I can see it.
You can see it. Yeah. All right, Born-Haber, maybe a little still challenging to see. Hess's law, add up the individual steps. The Born-Haber cycle specifically looking at, let's say, like the formation of a crystalline structure. Okay, so let's kind of break this apart slowly and methodically and see where we're trying to get to.
Do we need to write it down?
If you would, at some point, just in your notes say, make sure you can see this image on the PowerPoint or review it. The second handout, if you look at the handout you got today, there's one that says magnesium chloride, the Born-Haber cycle for magnesium chloride, right? Yeah, that one. This one that has a whole bunch of space. You're drawing this graph, this diagram for magnesium chloride. So having something to reference would be good. Okay?
Which one? Can I have one of those sheets?
Yeah. Good thing I printed like 60 of them. Is anybody else taking? All right, before we do that, we need to get a little more of the notation. Historically, this is the challenging part of this unit. It's not the math. The math is all addition or subtraction. It's literally the notation. Just like in the physics class, we have to decorate things. Same thing here. All right, so this is enthalpy. We know that. That was what we just expressed. This is the enthalpy of the reaction. Right? So it legitimately means when a reaction is carried out, what is the overall change in energy of the system? Right? That's what we're looking at, and specifically heat energy of the system. If we wanted to look at some notation like this, I'll try to say this carefully. This is the change in enthalpy of formation for a given compound under standard state conditions. I'll write this all in a second. You're going to say this like this: delta H naught of formation. This symbol naught is not like
Is the F supposed
not
to be a subscript?
F. Yeah, F, not S.
What is this supposed to be?
Yeah, subscript. Like nautical miles, think of it kind of like that. It's like a degree symbol. Fair? So delta H naught of formation.
How is it spelled?
Yeah, this is, I don't know. How is it spelled?
Like nautical, like N-U?
I don't know. I've never made this up. Yeah, Sierra Trading Post, STP, stands for Standard Temperature and Pressure. STP, standard temperature and pressure. When we get to gas laws, STP changes slightly. All right, now the question is, why is there such a thing as standard temperature and pressure? It's because under standard state conditions, you might be able to ascribe certain outcomes consistently under those conditions. So the standard state temperature is 25 degrees Celsius, which is approximately 298 Kelvin. What's the conversion between Celsius and Kelvin again? Do you remember? Degrees Celsius plus 273.15, right? So approximates at 298, a little above. And then the standard pressure is 1 atmosphere. ATM stands for atmosphere. Where on Earth, legitimately, are you if you're at 1 atmosphere?
Sea level?
Sea level. Yeah, anywhere at sea level, right? Death Valley, California, you have greater than 1 atmosphere. Top of Mount Everest, you have less than 1 atmosphere. Fair? So as you go up, the atmosphere gets less. As you go down, it gets even greater. So standard temperature and pressure. All right, back in the day, a week ago or so.
You said you were gonna write it down.
I will. Remember this? Do you have that table?
Oh,
If I can make more copies, or my computer froze. Don't freeze. Please don't freeze. No! Come on, computer. Oh, we are solid frozen, y'all. Dang.
You said it.
That's a true dream. Anybody need one of these though?
Yes.
Okay.
I don't have it.
Is it this?
Because I can't even turn her off. I'm pulling the power button. Oh, there she goes.
Oh, you're gonna like, oh, you're gonna shut it down.
I have to. You need one.
I don't
What I was going to show you is if you look on Google Classroom, it's also on Google Classroom under course material or reference material or something material. And I think I honestly put it in this chapter as well. I should probably keep one.
I have one.
Maybe kind of your share and tell me another copy. Can I?
Oh, wait.
Can I take that for a second?
You
I'll make some more copies. Can you guys share? Trevor, do you have one?
No, I don't. This is yours.
I mean, while the computers are starting, you could.
Good.
When were you supposed to have created this?
I think I handed out and they were not printed right.
I think you're right.
I printed more.
I don't think I've ever seen it.
Does that say 298K?
It does.
Yeah.
298.
Yeah. 0.15.
Thanks.
8.15. All right, so while this is booting, if you look at the, do you guys have two? Do you guys have two? Can you
It's
give one to Trevor for now?
273.
Do you mind?
Up on that equation.
Don't take it
It's
off.
273.
But if you look at this table, the only column that you're going to care about is the delta H of formation column. So it's this first one here. The Gibbs free energy and the standard state entropy, that's not you, that's Chem 3. So these two columns, delta G and S naught, not you. You want delta H of formation. Okay, this means that we're forming 1 mole of product.
Can you first write out what the equation is so that I can write that down?
Which one? Sorry.
The delta H naught.
Yeah, that's what we're doing here. Yeah. So this means you're forming 1 mole of product under standard state conditions from your constituent elements. Let me give you an example of that.
Wait, where is that supposed to be?
All right, so here's an example.
What is constituent?
yeah. If you have calcium, is calcium a solid at room temperature and pressure?
Yes.
Yeah.
Yeah.
You would not go ahead and say, oh, calcium is a gas at room temperature and pressure. Why? Because at center temperature and pressure, calcium is a solid. That is its constituent element. Calcium shows up like this. Calcium does not show up like this at room temperature and pressure, in essence, right? So we have to do some notation. What about this? Is this a true statement? That to form calcium oxide, you use calcium and oxygen, elemental form of oxygen. Is that a true statement?
Use O2.
Use O2, which is under standard state conditions. Oxygen normally expresses itself as the homonuclear diatomic molecule, which would be O2. What phase state?
Yeah.
It's gotta be a gas. You don't have liquid oxygen, intense amounts of pressure need to do that. So you would be saying, to form 1 mole of calcium oxide, you need to use the constituent elements. So in their pure elemental forms, how do they show up? And you derive that 1 mole of product. However, if you were to balance the chemical equation, we haven't really talked about that. We will come up. How would you balance this? 2Ca, right? You'd have to do something like this and like this. That's fine, but that takes away our 1 mole of product. So if you're looking at your sheets, this literally is defined as 1/2 O2 and 1 Ca. So can you have fractions? Yes. Has anybody told you that? I don't know, but you can.
No.
If you have half of an oxygen molecule, you have 1 oxygen, right? You with me on that? Yeah? So
Is
1
calcium
oxygen.
oxide solid?
What's that?
Is calcium oxide
Yeah.
solid?
Solid, at room temperature and pressure.
The
No,
product.
The product.
Yeah. And then here, that's what we're deriving. So when you look at your actual delta H of formation value for calcium oxide, go ahead and find that now on your sheet. You have different areas you can look. You can look at the calcium, you can look at the oxygen. I'm looking at the calcium and I see negative 635, right? 0.5. So we write that like this. The delta H of formation under standard temperature and pressure, so delta H naught for calcium oxide is negative 635.5 kilojoules per mole of that compound, right? What does the negative sign imply here? What's going on in the reaction?
It's losing it.
So it's exothermic, right? And in terms of quantity, because it's kind of an arbitrary value, like 635, is that a lot or little? But look at just some of the other things on that sheet. Does that seem like a lot or does that seem like a little bit of energy?
Whoa, a little. The sun.
It's probably mid-range, right? I mean, you have thousands, but you also have things that are zeros. It kind of seems like it's in the middle-ish of that sort of sliding scale, if you will. But big picture here, this is still for 1 mole of a product. So if we wanted to say, oh, 2 moles of calcium oxide and then balance the equation, what would we have to do?
Double it.
You'd have to double it. So that's part of the mental aspect of this chapter is if I need to do 2 moles, I double my enthalpy. If I need half a mole of that, I need to half the enthalpy value. If I need to reverse the process, let's say that like this. If I wanted to take calcium oxide and form calcium and oxygen atom, so the actual dissociation of molecular oxygen just to form the oxygen atom, how much energy would that require to reverse that process?
The same amount.
The same amount, but
But
positive. That means you'd have to be endothermic, so I'd have to be a positive value to make it go this way. Yeah.
So if you had 2 moles, would it change the value because it's in kilojoules per mole?
Yeah, you have to double it.
So
Yep.
it would be twice as many kilojoules
Yes.
per mole with 2 moles?
Right. Or if you wanted half a mole, you have to halve that value. Or if you want to triple it, you need to, or if you have 3 moles, you need to triple that value. And we're going to do some problems with that right now as well.
So even though it's per mole, so
Yeah.
as you increase the quantity
Yep.
of it, it's increasing the amount of
Yes.
energy per mole,
Mhm.
even though there's,
Right. It's like, I don't know if you ever in 8th grade burned a chip.
yeah.
Yeah.
oh yeah.
If you burn 2 chips, and those are exactly the same mass, exactly the same type of material, whatever heat was generated here should be the exact same amount of heat generated here. So if you burn 2 chips in the same container, you should get the same amount of heat as individually burning 2 chips, right? That's what this is saying. So if you produce 1 chip or burn 1 chip and do it a second time, you get double the amount of energy released in the process.
Even though it's like a rate,
Mhm.
like because it's kilojoules per
Yeah.
mole, so it's how many,
Yes.
How
She's
much
asking
per
how the
mole?
units cancel
how,
out.
yeah, how
and
did
then
the units?
Yeah,
Just
you
units
literally would
cancel.
say like, oh, I have 2 moles of calcium oxide, and now the units cancel. So you'd require double the amount of energy if you had double the number of moles.
Okay, so it wouldn't stay kilojoules per mole.
No, it goes to
Because then it would be
kilojoules.
kilojoules per 2
Right,
moles.
goes to kilojoules.
So the rate stays the same.
Yes,
Okay.
that's what you're saying. Yep,
Okay.
good.
I
Okay.
don't know. I'm lost.
Oh, we're gonna do some practice problems. Oh,
Wait,
was
you
it those that-
never wrote down.
Yeah, here. This is what this means.
No, you didn't like write out what you called it though.
Yeah.
Like, how do you say
Oh.
it?
The
Enthalpy.
actually out of your mouth, you should say delta. How do you spell not?
NAUGHT.
But is it that not the degree symbol?
But you
Is
tell
this
us.
how you said it though?
I don't. Yeah, this is how you're gonna say it. Delta, not.
Delta H.
Thank you. A formation
The, my connection's
What?
not
Stop.
good either.
for calcium oxide.
Delta.
So delta H naught of formation for calcium oxide, or you could say the standard heat
Formation.
of formation.
Wait, why do
for-
we have to put the for calcium oxide?
Just whatever you're describing for the reaction for calcium oxide for the production of whatever. So define what it is you're talking about. So delta H naught for the formation of calcium oxide, or this is the standard heat of formation for calcium oxide.
So it's the same.
It's the same
Same
language. Yep.
Well, now I gotta find.
If you're
out.
writing literature, you're going to say this. If you're trying to describe maybe the step-by-step process of where you should go to find this information, you would say this. So anytime you see the not symbol, you need to go to that tabulated thermodynamic quantities table. Anytime you see this not symbol. If you don't see the not symbol, then get out your other piece of paper, question mark. This one. I have one of these, so I think we passed these out. This is the average bond enthalpies. Yeah, I think you also had average bond lengths, but we don't need that one today. Average bond enthalpies. It says table 8.4 on it. You got it? Is it there? Does everybody have one? Good. Okay. 3 symbols. They all can mean the same thing. This means in general, consider the heat exchange, just in general. But you don't do anything different if you're talking about this or this. So this literally, I'm just going to erase because it just means consider heat exchange. You do something different. This means use that bond enthalpies table. And this is your thermodynamic quantities table. So that's where you go whenever you see the not symbol. However, if this reaction that you're defining is under standard state conditions, then it is perfectly fine to say that the delta H of the reaction is equivalent to the delta H of formation. And this is the key right there. If the reaction is under standard state. Then you too could also go use the tabulated values in the back. And the nice thing about using those tabulated values is the experiment's been done repeatedly over and over and over again. You just got to go get the information and throw it into the calculation, right? You don't have to define it any other way. So it's not that they can't be equivalent, but if this reaction is not equivalent, or the notation is not equivalent, then you're no longer at STP. You're at something like, let's say 10 degrees Celsius and 1.5 ATMs. You would have to define what that new temperature and pressure are, and therefore no longer are you at the pre-described 1 atmosphere and 25 degrees Celsius. Does that make sense, right? I mean, don't overthink that. This is just one state of conditions, and scientists have studied that extensively. This is, in the classroom, let's go ahead and just make up a temperature, make up a pressure, and carry out the reaction. Legitimately what we do every time we do chemistry. Whatever the pressure is for the day, we go with it. We don't be like, let's wait till Wednesday until the barometric pressure reaches 1 atm. It's like, we're just going to use the described pressure. Okay, so this is the bond enthalpies table. I'm going to argue that regardless of whatever one you use, the outcome should arguably almost be the same. Not exactly the same, but arguably close enough that you can be like, okay, I don't think I made a mistake. There is an equation for this. This is at the top of your chemical bonding exam review. If you're looking there, there's 2 fundamental equations. One of those equations is consider sigma. What's sigma mean?
1.
Oh, that's fair. But in terms of the mathematical operation, what is sigma telling you to do as a function?
We don't know. That's
Take a guess.
Signal was the.
Yeah.
Well, yeah, but this is capital. Isn't this capital sigma? I think it's capital sigma.
Sure.
Wait. How the heck I got
We don't know.
You're
You're supposed to be teaching us, not asking
I
us
just think
questions.
yes.
It's the bond.
Well, I already said that. Mathematical sum for standard deviation.
Yeah, there you go.
Oh,
So
yeah.
add up. It means add up. Add up all of the individual enthalpies for the products. Bond's broken. Sorry, bond's broken. The products would be here. Bond's broken. Okay. And subtract that from the
Yeah, you do.
individual enthalpy.
It just looks really weird because of how he writes.
What's wrong with my? What is it?
It's just like an E, but you.
Well, because like we do
Well,
this in
yeah.
statistics, but because of how you wrote it, it just looked really weird.
Oh my god, what are
You're
you
just like too
doing?
exaggerated.
Just make an E.
It's just like
Like a rounded E.
I feel like that's it. Bonds broken minus bonds
Is that in delta H?
formed. Yeah, I'll describe it.
This is how language changes over the years.
It's true.
You just, oh my god.
It's true. All right, so look at this. I think I accidentally or unintentionally left out the number of moles thing. So make sure you have N described in those equations on the top there.
That's an N, not an M?
That's an N and then an M. So N and M stand for the
Oh
number of
my
moles of those things. So N and M are moles.
They mean
feel
the
like
same
at this
thing.
point you don't even know
It's
what
like
you're
X
talking
It
and
about.
is.
Y.
It's N and M are moles.
But why would you?
I'm gonna get there. I'll get there. I promise. Let me just describe the equation and I'll show you the application of it. So add up all of the energy exchanges that occur when you break a bond. If you have multiple bonds that you need to break, that's N. Subtract that from whenever you form a bond, energy is released. How many of those bonds did you end up forming? Okay. Now, I promise this is the same thing as Hess's law. This is just totally a different form. Don't write this. I just want you to go on a thought experiment for a moment. If I say, what is delta H for the reaction? And I say that's delta H1 plus delta H2. If this is endothermic, and this is exothermic, then the sign convention would be negative and this would be positive. Fair? Whenever you break, so I'll just draw random bonds here. Okay, so this is methane CH4 carbon tetrahydride. Whenever you break that bond, you put energy into the system, or to break a chemical bond is energy released. So do you need energy to break a chemical bond?
Yes,
Why?
because if you lose energy, it doesn't really do anything. But if you put in energy, the energy will do things to the bond.
Keep going. We're there.
Break it. Something
We're getting there.
I just remember back about pressure would break it because it's more unstable. Something, I don't know.
If sigma 1s, if sigma 1s is lower in potential energy than either of the atomic orbitals that are not bonding, so if this is true, so this would be something like hydrogen binding to hydrogen. If this is lower in energy, is that meaning it's more stable than the individual unbounded hydrogen atoms?
Yes.
Yes. So if you need to form a bond, do you release energy?
Yes.
Yes. Is that always true?
Yes. You always release some sort.
I like it. Remember this thing? Which one's endo, which one's exo?
The first one is exo.
This is this little arrow from here to here. That's delta H for the reaction.
And then the second one's in.
From here to here, this is delta H for the reaction. Is that positive or negative? Where you
Positive.
began and where you end. That's positive. So that's endothermic. And then this is where you began, where you end. That's negative. So that's exothermic. Do you always require energy to break a chemical bond? This is reactants. This is products. How do you prove you always need that? So we proved it here, molecular orbital, lowered energy, stabilizes, releases energy. What about here? What on these diagrams tell you you always have to have energy to break a chemical bond?
The fact that you never start zero.
That's fair. Keep going.
Initial versus final.
Keep going.
So the reaction,
Which portion of this curve, hands down, says you always add energy?
the end.
The fact that it goes up.
Yes. The fact that always, when you're at reactants, there's always a, what would you label this arrow as?
Activation.
Activation energy requirement. The energy of activation is always there. So that's always to break a chemical bond requires energy. Which portion of the curve would always tell you energy is released when you start forming chemical bonds?
The
Second half.
second
Yeah.
half.
Here, right? That is the amount of energy released to form a chemical bond. It just happens to be sometimes it's not very much released, right? And other times there's a huge amount that's ultimately released. Okay. So we need to be able to keep track of that because back in this Hess law equation, when you see that positive and negative
You're
sign,
mean for that.
what's that?
Yeah, I'm done there.
Oh. Whenever you see positive and negative signs appearing in Hess's law, is this equation now the same thing here? Whenever you break a bond, positive or negative, go ahead. Positive or negative? Bond's broken. Whenever you break a chemical bond, that's a positive delta H sign. That's consistent with this. Whenever you form a chemical bond, that's negative. If you add a negative sign, is it the same thing as subtracting two positive values? No, right? So what we're saying is the expression of Hess's law is positive plus a negative is the same thing as looking at your tabulated values. So look at all these. See how all of them are positive? All of them? Every single one of these is positive. Does that mean this table is created to say how much energy is released when you break a bond, or how much energy is needed to break these bonds?
It's the same amount.
It's the same amount, just we need to do, this table is written to say how much energy is needed to break a chemical bond. So honestly, just put a negative sign there whenever you need to form a chemical bond. So these two equations are exactly the same, expressed the same way. So it doesn't matter to me whether you use this one or whether you use this one, whatever is easier for you. Okay?
So is the delta H of the reaction, is it always positive? Because
No.
it's a positive.
Yeah, good point. No, it doesn't have to be. And that would go back to those two curves where delta H for the reaction could be negative for exothermic and could be positive for endothermic. Those two individual ones.
So it's not always positive when the bonds are
No,
broken?
this is always positive. This is always negative. But if this value is like 10 and this value is 11, then delta H is
21. Because if you're adding, if you're subtracting a negative, then it's
but the
additive.
table, just leave, if we're using the table says 10. So take 11 minus the table value of 10. So 1, it'd be positive.
The negative sign in front of it is the negative.
What the negative sign
That's
is,
the minus.
so again, it doesn't matter to me which equation you use. If you want to use Hess's law and just add up all the individual values, that's fine with me because you have to introduce the negative sign. You have to. If you don't want to introduce a negative sign and you just want to use this table, then leave this subtraction sign. It compensates for any negative value that you ever would have had to introduce, and just use these values and plug them in as is. So this is taking care of the introduction of the negative sign in Hess's law.
So you're not subtracting a negative.
Right,
Okay.
right. It should
So
have
it should
been,
not say
it is a
It's
negative
already
value,
negative.
but we took care of that value.
So it's positive minus a negative, which therefore makes it positive plus
Right.
positive.
Right.
No,
So
no, no.
this
what?
negative
It's-
is no longer,
It's,
let me go with this.
the negative that he wrote on top is with the subtraction sign.
It's this is a weird analogy, but if you have an apple and it's red, right? And you want to be like, I want to make, it's stupid, but it's worth it. If you have an apple that's red and you don't want to deal with the red color of an apple, you just want to deal with the fact it's a circle, then you're going to just say, whenever you see a baseball, consider that to be an apple. I know, it's weird,
It's
right?
not red.
Because I know that's what I'm saying, is the negative sign is the same thing. You don't want to deal with the negative sign, so anytime you see a subtraction, consider that to have been a negative quantity originally introduced into Hess's law. So let's not try, I know I've overcomplicated it, let's not try anymore that you use this equation with the table tabulated values from this sheet, you get 100% the right answer every time. Don't make anything negative if you use this equation, because this is taking care of that. If you don't want this equation and you want to use this Hess's law, which is always an addition process, add up the individual steps, then you personally have to introduce the negative sign whenever you're saying bonds must be formed or broken, right? You have to keep track of that negative sign. So you'll get the exact same answer either way. Personally, I think this is a little easier so I don't have to worry about negative signs. Yeah? Yeah.
Okay.
But a little bit to Gloria's point is if the table says 11 and 10, this is going to be endothermic. Is it always going to be endothermic? Not if this is 10 and this is 11, right? Now you have an exothermic reaction. So there's no guarantee a reaction will be endo or exothermic. However, if this is a combustion reaction, now take a guess.
It has to be exo.
Yeah, I mean, combustion reactions generate a huge quantity of heat. So therefore, you know the bonds broken requires less energy than the release of energy upon the formation of new bonds. Fair? What about if this is, we haven't defined these types of reactions yet, I'm just curious. Do you remember what a synthesis reaction is in general? Yeah, it's like this. In general, do you think that takes energy or removes energy from a system? So like,
Right?
I mean, yeah,
It takes.
this. Yeah, it takes energy. And that's what we're trying to, next slide, that's what we're trying to get to here for the Born-Haber cycle. It would require a huge amount of energy to do this unless there's some chemical properties of distance. Actually, how close are these ions together? So there's no guarantee this should require energy. We need some additional information. Let's try that now. Born-Haber cycle. Oh, and then the second reaction for this one, or equation for this one. This is the standard heat of formation is equivalent to the bonds broken, or products, sorry. Products minus reactants. So in our example of, go find this right quick, just for argumentative point. Go find this on your tabulated values of thermodynamic quantities. So find delta H of formation for calcium. What do you see?
Solid 0.
It's 0. What about for oxygen?
Oh goodness.
Molecular, O2, as a gas. What do you see on those values?
Oh, I see it. Okay, 0.
It's 0. Look at any atom that appears on that tabulated value sheet as it would appear at standard state conditions on the periodic table. So if you find hydrogen gas, that's different. That should be 0. If you find calcium, we said calcium. If you find iron is 0, nickel is 0, so on and so
Lead.
forth. Any elemental form is 0. That means it's the standard. It's where you start. No energy is needed to make the constituent elements themselves because they are the elements. They're just there. They're the ones that are formed. To make these products, we combine the two together. So back to the point of, is this always going to be an endothermic reaction or exothermic? You don't know. You almost need to do the experiment to see what the result or the outcome is. And that's totally dependent upon the stability of the molecular orbital diagram or the crystal lattice structure, because this is an ionic compound, right? A metal with a non-metal binding together is no longer a covalent compound, so is the network itself very, very, very strong or not? Let's prove that using this one. So this is again on the PowerPoint, and this is what you'll be doing for that magnesium chloride thing. Let's kind of take this step by step. Okay, so start here. This is Na solid plus 1/2 Cl2 gas. Are those constituent elements? Na solid and Cl2 gas?
Yes.
Yes. If you go to the back of the tabulated values under standard state conditions, what is the delta H of formation for sodium solid? Don't overthink that.
0.
0, because it's the elemental form. What should be it for chlorine gas?
0.
0. Now, go to the back of the table and find NaCl as a solid. What do you see? Delta H of formation for NaCl,
No, it's right here.
negative 181.
If it's a gas.
0.4. So there's our result. That's it. That's our answer. That's what we should get at the very end of all of this tabulated stuff. You can use that table as a comparison or as a guide. That's the official answer, what we should have here. Notice that we get something slightly different. It's like, wait. You guys got 181?
You got
410.
Yeah.
Oh yeah, here it is. 411. Yeah, as a solid, right? Oh, that's a good. Bring that up
Negative
tomorrow.
410.9.
Tomorrow.
Yeah, bring that up tomorrow.
Why?
That's a good question. I like that. We'll talk about that tomorrow.
What?
No, not now, but later.
No,
I mean, I'm
confused
trying to
what you want us
solidify it.
to ask.
Just say, Morgan, why did we get 181 for sodium chloride gas
No, we
versus
know
salt?
why.
No, let
Oh.
me describe it tomorrow. Yeah, that's it.
Okay.
There's two different values, one for gas and one for
Yeah.
solid.
I know,
I know, but why the difference though? Okay.
because
It,
atmosphere, this, you said it earlier. Is,
yeah, it's where you fall on this graph. Yeah, but tomorrow, okay.
Fine, whatever.
All right, so this is what we should get at the very end, right? Your table predicts that. We could, and as simple as that, answer this entire question. However, this is the Born-Haber cycle. Let's see another method to get there. Okay, what occurs to go from solid sodium to sodium gas? Use words to describe that. What did you do?
Energy into it.
You put energy into it. How do we know that? Because this is a positive value. That's the amount of energy needed to do
And
that.
don't you had heat?
You did. That's enthalpy, yep. But what phase transition? What word do you use to describe solid and gas?
It's
No sublimation.
Sublimation.
yeah.
So you are subliming, right? You're going the process of sublimation in essence to go from the solid sodium to the gas. You add enough heat to do that. You totally bypass the liquid phase state, which is good. Then notice that nothing changed for the chlorine, right?
But it's still gas.
However, if you look here, nothing changes between sodium. You totally deal with chlorine. Did you see that? Oh, tried doing it twice. I didn't even look. I just caught. Nothing changes from sodium to here.
You're turning into Davis.
So we focus on sodium at this position. Don't deal with chlorine. Now we deal with chlorine. What changed to go from here to here?
The 1/2,
What does that mean now?
like it doubled. So, well, I can't see the thingy,
Yeah.
but there's no 1/2 anymore, so that means there's double the amount.
How many chlorines do we have here? Don't overthink that.
Or
It
one.
says
Sorry.
half.
Technically, so it's one, and then I just like simplified it.
Yeah, you simplify it. So in essence, what we're doing is we're legitimately taking the chlorine-chlorine bond and severing it. That's called the dissociation, or another word is atomization. In essence, you're just breaking that chlorine-chlorine bond. Now go to your bond enthalpy table, this one, and look at chlorine-chlorine. What do you see?
One side.
That should be how much though?
0. Chlorine.
No, this table, the bond enthalpy. 242. 242 here. Why do you see a difference in these numbers?
Because it's endothermic, because it's gaining the energy to break this.
Okay, that's fair. We're adding energy in to break the chemical bond, but why 122 and 242?
One is already bonded and the other isn't.
Say it again. What'd you say?
I'm taking a guess. I don't know.
Yeah, I don't know what you said though.
One is bonded and the other isn't.
Yeah, is that table breaking this table for 1 mole of chlorine atoms? 1 mole. To break 1 mole requires 242 kilojoules per mole, right? How many moles?
Half it?
Yeah, there it is. We have half a mole of chlorine. Whenever we balance this equation, we don't need 2 chlorines, we need 1 chlorine.
Well, then wouldn't it be 1?
1 chlorine is half of this, yes?
Yeah, but
Right.
wouldn't it be 121?
Close enough.
Yeah, we rounded. So 242, half of that, 122. Can you see that? This value is for 1 mole, and we only need half a mole. So this is the amount of energy needed for half a mole of this to break, to separate. Now, what changed as we move from here to here? So now we focus on sodium, we focus on chlorine, now we're back to sodium.
There's a plus sign, I think. I can't.
Well, they separate. They took out the electron.
Yep, what do we call that?
I know.
Words.
I don't know.
Yep.
Oh, it was right? Oh my god.
How many electrons are we removing?
Wrong one.
So it's the first ionization energy. Don't give me a number, give me an idea. How much energy would be needed to remove the second valence electron of sodium?
A lot more.
Like how much?
Like A lot.
Like the same amount as to remove neons?
Yeah.
Yeah. Because neon would have the same electron configuration as well. Okay, is it true that to sublime is endothermic, to break a bond is endothermic, and to remove an electron is endothermic?
Yeah.
Yes. Now, this is exothermic, right? Delta H is getting to be a negative value. What's occurring now? Chlorine to chloride,
You're adding one electron.
right? So this is chlorine plus 1 electron turns into chloride. Give me a word, periodic trend, that describes that value. Periodic trend.
Atomic radii
Keep going. That's
is
it.
now.
The trend, the definition is the amount of energy released upon the addition of an electron.
What?
Electron affinity. Good.
Oh, yeah, okay, yeah.
So the cool part about this, putting it towards is, you can look this up in a textbook, internet. You can look this up on the internet. You can look this up on the internet. You can look this up on the internet. None of these values you calculate. They're all given to you. You just have to know where to plug them in at ultimately. And then now you're here. If sodium and chloride are going to form sodium chloride as a solid, sodium ion and chloride ion, look at, and this came back to the question we just had. Can you predict how much energy is needed, endo or exothermic, to go from the original constituent elements to the end? Follow my marker.
Oh my god, the curvy thing.
It is the curvy thingy. Is that endo or exothermic?
That's exothermic.
That's endo.
endothermic.
See it? Isn't that kind of cool?
That is
Right.
kinda cool.
So you just make this the potential energy axis, and you say my reactants, which you have here, and my products, which you have here. That looks to be an endothermic reaction. If you wanted to make table salt cheap for the American consumer economy, guess how much money that process would take?
A lot.
A lot. Why?
Because you're doing it a lot of energy.
Because you have a huge amount of energy to get out table salt, but you can go to the grocery store and buy like 10 pounds of it for like $2. So what does that actually mean about the process?
It must be exothermic.
It's exothermic. So no longer is that line there, it's actually here at the bottom. Notice that now this value is delta H for the reaction. Delta E to formation for the reaction. So now we have a slight, just conceptual problem. Think about this, don't draw it necessarily. Remember when we did this curve so many times before? We said if you have the best distance between two atoms, so if you take sodium ion and the chloride ion and interact them together, that's the best distance away. R is the distance away. What is happening as you go this way again?
Energy is building.
Because what are you doing with these ions?
You're pushing them closer together.
You're smashing them into each other. You're trying to fuse them together to become one atom new. That's like on a star. What are you doing over here?
You're getting
Pulling them away.
You're trying to pull them away, but they don't want to be away, right? Because they're like a magnet. They just want to be together. And you're like, right? And then eventually, as you rip them apart completely, if this approximates an asymptotic curve to infinite, or 0 nonetheless, you would take the integral all the way out as it approaches the value of 0. That's your boundary condition in calculus. Then this would mean if these two things are infinitely far apart, go ahead and put that down in your notes. If there is no distance of a force of attraction between them, then this entirely would be an endothermic process. But if you can move those ions close enough together, a huge amount of energy is released in the process. Huge. Like legitimately, you put this in a container with chlorine gas, it literally catches fire and starts sparking like one of those fireworks sparklers would end up doing. Very cool reaction, very dangerous though, because of the chlorine gas. And then this value here. If we made that positive 787, this is the lattice energy. By definition, the lattice energy is the quantity of energy needed to take 1 mole of a solid substance and turn it into 1 mole of its gaseous ions. That's lattice energy. 1 mole of a solid substance and turn it into 1 mole of its gaseous ions. It requires a huge amount of energy to do that. So what's the negative sign mean?
I mean,
It's the amount of energy released when you take one mole of gaseous ions and you form a stable crystal structure. So what you eat is actually, remember John Wynn was trying to help me draw my three-dimensional structure? Remember this? I put sodium ion in here and I put the chloride ions outside everywhere, and then we all booed me for not being able to draw. Remember that? Yeah, you have something like this. This is what you're eating, is this arrangement. To form that arrangement over and over and over again, to do that releases a tremendous amount of energy in the process. So honestly, look this up on the internet, throw them in there and add them all together. And that's where we'll end today. So let's add them all together. Delta H4, I'm going to say sublimation. So let's say delta H4, the reaction, is delta H sublimation plus delta H, this is atomization or dissociation, plus delta H, what? First ionization energy. I'll call it 1 first IE plus this one, delta H.
I can't even see what that says.
This is electron affinity, so I'll call it EA, plus, what's here? The lattice energy, but not.
So negative
The negative of lattice energy, right? So you could call this, what's the official term? I'm going to call it crystallization. So to form that crystal, what is it? We said this is endothermic, so that's positive. Breaking a bond is endothermic, that's positive. Removing an electron, that's positive. Adding an electron, that's negative. And forming new stable bonds, that's also negative value, right? So notice what you have here. Are these bonds broken? Would you summarize this as these are all, everything in essence that's broken? And this is everything that is formed. Or you could summarize that as this is all reactant stuff, reactants, and this is all products. Hence, those two fundamental enthalpy equations that are written at the top of that sheet to begin with. So take Hess's law, this is Hess's law, and just add all the individual steps together and you get the outcome at the end. The difference only is this is the not symbol, so at standard temperature and pressure, fine. We have something to compare it to ultimately. So we would plug in this value of 107. I'll leave out the units for the sake of simplicity and time here. This would be 122, 496. This is negative 349 and negative 787. Right?
You made a formula.
Isn't that sweet? And that's the same thing you would get in the back of your book, or the back of the tabulated values as well. Straight up. That's legit. That's science.
Why is it
Actually, I'm gonna just put it up.
Okay. Why don't you guys try the magnesium chloride one?